Alright, we're interested in defining equations of lines in 3-space. Before we do that, let's remember how we did this in 2-space. So if we have an XY coordinate system and we have a line, remember we need to know two things. We need to know a point on the line, we'll say x1, y1, and we need to know the slope of that line. And if we know those two things, then we can use point slope, y minus y1 equals the slope times x minus x1 to come up with the equation of that line. Alright, we want to extend this idea for lines in 3-space. So I'm going to clear my board so we have a fresh space to work with. So let's draw a pretty big, here we go, three-dimensional coordinate space. So that's x, that's y, and there's z. And let's have a line, and we'll call that line L, that lives in 3-space. And this time, what we know is a point on the line, we'll call that P naught, with coordinates x naught, y naught, and z naught. Okay? Good. And we know the direction of this line. And what does that mean? Well, we know some vector that is parallel to that line. So let's say that v is the vector that we know. So let v be a vector that is parallel to my line L. Okay? And for ease, let's make that right there. So that's my vector v, and I know my point P. Now this is all I need to be able to define that line, but we need a few more tools to work with. So let's pick an arbitrary point now that lives on my line, and we'll call that just point P with coordinates x, y, z. So these will be my arbitrary values. And notice that the vector, let's put that into a different color, between P naught and P, we'll call that vector A, so it is the vector defined by P naught and P. And notice that it is parallel to my vector V, which means that A is some scalar multiple of V, right? Two vectors are parallel if they are scalar multiples of each other. Alright. Now let's define or draw two position vectors to my 2 points on my line. So the first one, which we'll call r naught, is the position vector to the known point P naught, and then we'll say r is the position vector pointing towards my arbitrary point P. Now notice that r is equal to the sum of the vectors r naught and a. Right? That's our vector addition. R naught plus vector A gives me R. And if we want to write it in terms of the vector that we do know, V, this becomes R equals R naught plus TV. And this is my vector equation of my line L. Okay? So my vector equation, notice, has a parameter of t. Now, I'm going to go to a new board here, and we're going to talk about writing this in parametric form. So remember that my vector r can be defined by its coordinates, its position vector. So x, y, z is another way to write my vector r, equals x naught, y naught, z naught, because that's my vector r naught, plus t times my vector v, okay, which we can say is a, b, c. We just arbitrarily made that up, and that is fine. Well, what does that mean? That means that I can write this as, this vector x, y, z as x naught plus at for the x-coordinate, y naught plus bt for the y-coordinate, and then z naught plus ct. Now that's still a vector equation of the line, but what we discover is that x is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus zt. And these three equations are called the parametric equations. And that's with my parameter t, parametric equations of the line L. So on this board, we had the vector equation of my line, and it's defined entirely based on the position vector of my known point plus a scalar multiple of my known direction vector. And by manipulating the coordinates and rewriting them just in each component, we have what's called the parametric equations of my line L as well. Perfect.